Hello, Chem 1B. This is Chapter 22, Lecture Video 7, and we're going to be talking again about crystal field theory. So, one of the things we learned back in Chem 1A, which was known as the off-bow principle, is that we always add electrons to the lower or energy orbitals first when we fill them with electrons. Now, in this chapter, we kind of need to put an asterisk next to this. There are exceptions to that statement, and we need to know when and when not to follow this rule. So let's talk a little bit more about this. So when we're filling these d orbitals that we've been talking about, we fill the ones that are at the same energy with one electron before pairing anything up. And this one's called the Pauli exclusion principle. Again, something we learned in Chem 1A. We put a single electron in each orbital that's at the same energy before we put any together in the same orbital, right? So I always like to compare this to, if we have two rooms and two roommates, they're probably not going to want to live in the same room. They're probably going to want their own room by themselves before we pair them up. Whereas if you're in a house with only one bedroom, yeah, those two people are going to live together in that same bedroom by necessity. So we only pair up electrons until we absolutely have to. Now, this is what we call a low spin complex when everything's paired up. In another scenario, and this is where this rule is kind of as an exception, sometimes when the gap between our orbital energy levels is small enough, we fill all of the empty orbitals with one electron before pairing any of them, regardless of whether they're at the same energy or not. This is what we call a high spin complex. So if we look at these two examples, right, here are two d orbital diagrams, one with the ligand as cyanide, which is a strong field ligand. In other words, as you can kind of see in the picture, the delta O is much bigger here than water, which we usually consider a weak field ligand, where this delta O is kind of small. Now, in both of these complexes, we need to figure out how many electrons do we put into our diagram, and that number, however many electrons we put in, is always based off the metal ion in the compound, which in this compound, in both of these compounds, is Fe2+. So we need to figure out how many d electrons are in the electronic configuration of Fe2+. So I would write Fe first. So this is Ar, 4s2, 3d6. Right? And when we go from Fe to Fe2+, we lose 2 valence electrons. In other words, we lose these 4s2 electrons because they're in our valence shell, and the 3d electrons are not. So this 6 here is how many electrons I'm allowed to put into these two diagrams. Now, how we put them in is very different because of this one being a low spin complex and this one being a high spin. And this is related to specifically the ligand that we're dealing with. This is a strong field ligand, and this one is a weak field ligand. So the strong field ligands, they're going to split your d orbitals more, as you can kind of see here with this guy, than the weak field ligands, which barely split it as much, half as much in this example. Now, because of this big gap between energy levels, we fill these two orbital diagrams differently. Now, for the strong field ligand, we're going to put one electron up first, then due to the Pauli exclusion principle, our next one goes here, and the next one goes there. Now, I've put 3 of my, again, 6 electrons that I'm allowed to put in this diagram. Now, because of this energy gap to get up to here, the next one's going to go here. And so we're obeying what we call the off-bow principle for our strong field ligands. And this is my d orbital diagram for hexacyanido ferrate 2. That's the name of this complex ion. This is the d orbital diagram for it. Now, Fe with the 6 waters, or in other words, hexa aqua iron 2, this compound here is different because as a weak field ligand, our d orbitals are not split as much. So in this scenario, when we're filling, we do same thing. We obey the Pauli exclusion principle. But here's where we disobey the off-bow principle. These next three electrons would, or the next two electrons would rather not pair up here. They're going to jump ship, go up to the top. And so we put one electron in every single orbital regardless of the fact they're at different energies. Now we can start pairing electrons up, right? So we put the next one down here. And so depending on how big your splitting is, we may have filling all the same energy levels, obeying the off-bow principle, which is, this rule here. Or we may disregard the off-bow principle due to the fact that it is a weak field ligand. Something to remember from Chem 1A is magnetic properties. When you were in Chem 1A, you probably learned about para and diamagnetic substances. We can actually predict whether a complex ion is going to be paramagnetic or diamagnetic, or a coordination compound, same difference, is paramagnetic or diamagnetic based on these splitting diagrams. Remember that in a diamagnetic compound, these definitions aren't changing from Chem 1A. There are no unpaired electrons. All the electrons in a diamagnetic substance are all paired up. In a paramagnetic compound, we have at least one unpaired electron in the compound. So if we look at these two orbital energy diagrams for the D-splitting, or crystal field diagrams is another name for them, they're both octahedrals. F- is a weak field ligand, hence the smaller delta, or the smaller splitting energy. Cyanide, like I said earlier, is a really strong field ligand, so a very large splitting energy. And if we look at cobalt, in this compound, it's 3+, and in this compound, it's 3+. So if we look at cobalt 3+, we can say, hey, that's going to be 4s2. If we just lose the 3+ for a second, it's argon 4s2 3d, sorry, 3d7. Once we have this 3+ here, now we need to lose some electrons. The first two are the 4s, and then we got to subtract one more, so it would be Ar 3d6 again. And so because we have these 6d electrons, notice that both these diagrams have 6 electrons in them. And that's how we figure out how many electrons are in our diagrams. Once we know that, hey, I know cobalt 3+ has 3d6, so CO3+ is 3d6. Then I know I need to put my 6 electrons in here. So 1, 2, 3. Whoops, sorry. I wouldn't. The order we'd fill this one in, since it's such a weak field ligand, 1 up, 1 up, 1 up, then go 1 up here, and then the 1 down. Over here, because of the big splitting energy, we go up, 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 and then down, 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 all in the bottom part. Like so. Now, at the end of the day, we can classify these as two different things in terms of their spin. This is the high spin. This is the low spin. In addition, this is a paramagnetic substance, and this one is a diamagnetic substance, which you can kind of see here. All right, so let's do some problems here. We're going to draw the d orbital diagrams for these four complex ions, and they're all octahedrals. And I know they're all octahedrals because each one has 6 things attached to it, right? We got 6 of them here. 4 plus 2 is 6, 6, 6, right? So we got 6 things attached to each one of these. They're all octahedrals. So let's do A first. I'm going to draw out my 3 down d orbitals, and then we got to draw the other 2. Now, CO is on the higher end of my ligand field strength, right? CO is one of the stronger field ligands. So this gap needs to probably be bigger than I've drawn it, right? So it should probably be more like this. We have this huge gap between the d orbital diagrams. Now the next thing I need to do is I need to figure out, hey, how many d electrons do I have? I need to figure out that from the iron based on the fact that carbon monoxide or carbonyl is neutral. We have a 3+ charge on the complex. This is Fe3+, which is Ar 3d5. And so we have 5 d electrons that we're allowed to put into our diagram. And because of this really strong field ligand that we have attached to it, I'm doing this, right? This is a low spin complex, and that's due to the strong field ligand. And finally, as you can see here, we do have 1 unpaired electron, so this is a paramagnetic complex as well. And so this is the d orbital diagram here. So let's look at B. I'm going to do it down over here. We have cobalt, we have water, we have carbonyl. There are 2 carbonyls here, and we have 4 waters here. So the splitting energy, because we have less COs and more of a weak field ligand, H2O, is definitely going to be a smaller delta O than this first one that we had done. So 1, 2, 3, we're going to say it's about that tall. Again, this distance between these has to be smaller because we have a lot of a weak field ligand, which is water. Now, in this scenario, it would be kind of hard to predict whether this one's going to end up being low spin or high spin. I'm going to err on the side of the fact that we have 4 weak field ligands here. So we're going to err on the side of high spin. So again, I need to figure out what my cobalt's charge is. This is CO3+, and I need to figure out my d orbital electron configuration so that I know how many electrons I can put in my diagram. And so our electron configuration for cobalt 3+ is argon 3d6. I have 6 electrons that I'm allowed to throw in here, and I'm going to start by putting 1 up, 1 up, 1 up down here. And because we're going to err on the side of high spin due to the large number of weak field water ligands, we're going to go up, up, up here. And I got 1 more, goes down there. So this is the high spin version. It is still paramagnetic. And again, high spin due to weak field ligands. You could, in this type of problem, I would probably either tell you which one to draw, high spin or low spin, or I'd ask you to do both. So in this case, I drew the high spin. You could draw the low spin on your own time if you wanted to. So C, kind of keep switching colors here. C, we have cyanide, which is a very strong field ligand. It's like one of the strongest. So this is probably going to have our highest splitting energy. And again, it's cobalt 3+ because I have 6 cyanides, each at -1. And it's a 3- charge, so the cobalt had to be 3+. So this tells me that I have 6 things. There's no question they all have to go down below. This is going to be a low spin complex. And we have a diamagnetic complex here because none of the electrons are unpaired. And again, low spin due to very strong field ligand. All right, lastly, we have letter D, which is Cl. Cl is a very, very weak field ligand. So I have my 3 first diagrams and the orbital, 3 first d orbitals low, and then there's barely a split between these because the delta O here is going to be very small because of Cl being such a weak field ligand. This is still CO3+, so I still have only 6 electrons to put in this diagram. It's definitely going to be a high spin complex. So 1, 2, 3, 4. Oops. The 4th one shouldn't be there. It should be up top. 4, 5, 6, and this is definitely paramagnetic. And again, high spin due to very weak field. Ligand. All right, so as always, if there's any questions about how to do any of these, please come to discussion sessions or email me or get a hold of me somehow.